Test, test, test. That's showing up. It's not the right microphone, so the EQ might be a little screwed up. I do apologize, but for some reason the other microphone is not wanting to work. So, what is up, everybody? It is SysAdmin Sean here, and we are running a live stream, which we don't do very often, but we do it from time to time here. And today I wanted to talk about security, server security, networking security, basically kind of a primer to how you should handle your security in your infrastructure. If you're a small medium business, if you're an enterprise, if you're, depending on how your offices are and things like that. And I've kind of got a big diagram up here, and it's a lot of stuff to look at. So we'll be zooming in and out a lot. So I hope that that's pretty enjoyable. I'll try to keep an eye on chat to make sure that I see when people send messages, but sometimes I'm not very good at that, so we'll just have to see how it goes. But I've got that up there. I want to double check one more time. Yeah, everything's running. Let me know if you can hear me okay. Hopefully you can. Everything looks like it's loading at least, so I don't know what was going on with GG Leap, but whatever. Anyway, so all of that to say, that clipped. I should probably dial that back just a little bit more. Make sure the filters are on there. Let's get a noise gate. Yeah, that looks okay. Okay, so anyway, we got that going. We've got our diagram up here. Let's talk about kind of the basics of security. The stuff that you probably don't realize kind of falls under that net, but it's just good practice, and the good practice leads to better security overall. Somebody had asked earlier for me to start doing some videos on security and alerting and things of that nature. And so if we really want to start that discussion, we need to start that discussion at the beginning. And that's really what you're hooking up to your network, because that's really, if you don't have a network, you don't have to worry about IT security because there's nothing on your network. So you don't have to protect anything. But you're going to have a network, and you're going to have devices on that network. And you're going to need to organize those devices on your network. And you're going to need to organize your networks that those devices that get on those networks connect to. And that's what we're going to be talking about, is planning and organizing your network beforehand so that when you are deploying all of these different pieces, you do the right thing. So let's zoom in a little bit here. So obviously you have your data center, and then most folks these days would know that you would have a data center firewall and a border firewall. And your data center firewall would protect your servers and your network equipment inside your data center. Your border firewall would protect everything else from the internet. Pretty simple, right? Makes sense. So we've got our data center here. It's got all these different types of servers in it, right? So, and it's got networking equipment in it. So we've got servers. We've got, this was apparently a supercomputer, so we'll call this a supercomputer. There we go. We'll move this out of the way, and this out of the way, and this out of the way. In case anyone's wondering, this is draw.io. I love this. This was listed as proxy servers for some reason. We'll put that in there. This was web servers, right? And then this is, so we got regular servers, we got that. Let's say this is database servers. Let's say this is storage, okay? So we've got a few different servers here inside our data center. So we'll connect those real quick. Bloop. And we do multiple bloops. Bloop. Not really how I want to do that. Bloop, but whatever. So on and so forth. So that you have all your connections going, blah, 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 blah. I don't like the way that looks, so I'm going to mess it up. Now, all of these things live inside your data center. That means they get protected by your data center firewall. So this firewall is configured in a way to only allow things in and out of your data center that need to talk to your servers, because not everything in your environment, like so here, would need to talk to everything in here. It wouldn't need to use, any of this network and configuration equipment. None of that's important. You don't have to worry about that right now. But if stuff needs to get in to the data center, then if it's on-prem, which is what we're going to call, let's move our border firewall out. This will be geographically poignant, but not make a lot of sense. Visually, it will make sense, but realistically, it won't make sense. So your border firewall protects your border, right? Everything here is behind your border firewall, which goes out to the internet, because you're going to need to go out to the internet for things. Now, after you're past this step, either stuff comes in from the internet to your data center firewall, to your data center, or it goes into your border to your clients, and then your clients may go into your data center firewall, and so on and so forth. Hey, what is up? It's going well. It's going well. I hope you tuned in to learn a little bit about network diagramming and creation and enjoyment. So that's what we're going over right now. So how do you organize all of this traffic? So for a lot of folks, you're probably used to, let's say, an internal network 192.168.0.0/24, right? That's probably the kind of network you've run personally. It's a /24 network, so you'll have, for instance, if it's a /24, you're going to have a gateway like 0.1, and you're going to have the subnet mask of 255.255.255.0, which essentially gives you the IP addresses 192.168.1.0.1 through 192.168.0.254. And by default, all of those devices can talk to each other, right? Anything that's on that network can communicate. Computer 1, if this has .1 and this has .254, they both know to talk to, well, really, this one probably won't have .1. Let's say this has .2 and this has .2. Yeah, 254 is okay because 255 is going to be your broadcast address. Okay, so let's lay this out a little bit better. This is your gateway, right? This is the device that usually handles all the routing, all the configuration stuff. And then you're going to have a broadcast address, which is going to be like 192.168.0.255, right? That just means we'll call this the broadcast. That IP address, these two IP addresses, consider them gone as part of a subnet. If you have a realistically good network, consider them gone. That's just a simple way to think about it. They do functionality, and it's important to know. But for the sake of this video, we're not going to talk about that right now. So let's say this is 192.168.0.2, and this will be 192.168.0.3, right? So because they both live on this .0 network, this 192.168.0 network, then they can talk to each other, no problem. Bloop, cool beans. But what if we change this and move it into that network? So that would be a different subnet, essentially a different network. Without another piece, basically without the gateway 192.168.1.1 communicating with 192.168.0.1, they can't really talk to each other. Doesn't work. And again, that is the basic general description of what's going on there. There are technical terms for that. But what you should know is those two networks are isolated without communication between them to understand how the routing works, to understand who exists where, who the head is, because at the top level, there needs to be something saying, all right, that network, this network .0 can talk to this network .1 because I allow it. That is organized and allowed. And that is usually done, that's right, in your data center. So in your data center, you will have routers that dictate out. Usually they're called like core switches. We're going to keep terminology pretty simple. There will be a big piece of network equipment located usually in your main data center. That piece of network equipment will know all of the networks, or at least the majority of networks, for the buildings that attach to that piece of the data center, because when you get down to brass tacks, the real connectivity is fiber from the internet will come into your data center. It will then, that's where the border firewall really lives. Usually your data center is where your fiber terminates. You could have it in a different building depending on geographic location and cost settings and things like that. But let's just say it goes to the data center. Let's keep it simple. We've got our one data center. Our internet comes in. It comes in on our border firewall. This connection goes into the network equipment in the data center, right? So we'll do that. And then that connection goes out to all of your buildings to give them, why is it giving me shapes? It's weird. To give them connectivity, right? But at the same time, this piece of equipment and other pieces of equipment in your data center need to know what networks you have inside your business, so that it knows how to route that traffic outbound too. And that goes into a whole other thing about traffic routing and BGP and things like that, but we're going to keep out of that. So how do you decide how to organize these networks? Okay. This is the first part of the actual security discussion. You have to organize your networks or you're going to have a bad time. Let's get rid of all this info. So let's look at our options up here. So let's say we have 3 buildings, okay? And then we have a data center over here in a different building. How do we want to, do we want to just give these buildings the same network that the data center has? Absolutely not. You want to isolate your networks. You want to segment your traffic and organize it in a way that makes sense. So let's do that. Let's start off here. What we're going to do is, and this is going to make a little bit more sense as we go, so stay with me. Let's say that building 1 is going to be, and we'll use an internal range that a lot of places use. So some places use 10 dot, some places use 172 dot, some places use 192.168. I like 10. I don't know why, but I like 10. So let's say we got building 1. Let's do 10.1.0.0, and we'll do a slash. I guess that would be a /8. Let's find out real quick. Cider calculator. If I could type. There we go. So that would be a 24. Let's do /8 and see what we get. So /8 would give us, ooh, really? We should do our /8 at the data center and then divvy those out. So we're going to do this as a, we'll do this as a simple one. We'll just keep it simple. We'll do /24. So that's what people know. Okay. And then building 2, because we want to keep kind of a scheme going on here. So we can use the network as a way to organize what we're working on. 10.2.0.0/24. And then building 3, you guessed it, 10.3.0.0/24. Okay. So now we've got our 3 buildings labeled out and we have a network. This isn't 100% accurate. But those are our buildings, okay? That's what we decided to begin with. Is that going to be enough networks? Probably not. Because realistically, when you get down to it, you need to be able to do probably 16s. Let's go back in here. Let's do 10.1.0.0/16. Calculate. So that's going to give us the ability to set all 255s on the 3rd octet. And that might be a little big, but that's going to keep us a little bit cleaner. Because I'll show you what we have to do next. So that would mean that we can essentially set 10.1.1, 10.1.2, 10.1.3, so on and so forth. And why would we want to do that? Well, we want to isolate our traffic within the building. We don't want to give everything in the building a 10.1.0 address because we don't want all of these different devices talking to each other. We don't want our users, on the same network as our printers, as the same network as our HVAC. I'm going to call this HVAC even though it came up as UPS. We don't want it on the same as our APs. This is an AP. And we don't want it the same as our network equipment. Oh, wow, really? Yeah, we can do that. Cool. I'm learning draw IO as we go. Okay. So now we've got all this stuff that we have to organize, and this is our Wi-Fi range, and that's a whole other thing. So let's do something simple here. So let's say we got security cameras. Okay. So let's do those on 10.1.1.0, and we'll give that a /24. We're not going to have more than 255 cameras in the building, we're going to assume. That's a terrible, terrible, risky thing. And then now we've got VoIP 10.1.2.0/24. So on and so forth, all the way down. So we've got .1, .2, .3, .4, .5. This is probably going to be your biggest one. So this one would be a much larger amount of network addresses. So you'd probably have to do .5, .6, and .7 there. You know, .8, .9, .10, and .11. And you might even be able to get away with putting your APs on the same as your networking equipment, just because it's all for network management. And then your user workers here, they would go on another network as well. So we've built out our building networks. How wonderful. So now, if we get all of this proper traffic organized, then we know how to route it properly into the data center. So when we're building our data center firewall rules, let's say we need our users to get into the data center for any number of reasons. Maybe they need to get to an internal web server. So can we do that? Oh, wow. Yeah, let's say internal web. Let's say they need to connect to, what else? Oh, the file server. If you're running local file servers, maybe they need to hit the mail server. These are all different ports that you need to be able to allow into your data center. And so the data center says that traffic can come in via whatever these ports need to be and go into the data center. And then on the inside, we make sure that this says, all right, they're coming in to whatever networks we've configured for your servers on those specific ports for this network. Why would we do all that? Why would we go into all of this work to get all of this working, as opposed to just giving it one big network and attaching everything into that same network? So that we can control the traffic. We know who's coming in where and where they're going. So let's do a nice small example again. Let's say we have, let's grab this. Let's say we got user A here, right? User A needs access to the following things. Website 443. They need access to Active Directory. We'll do 389/636. We'll cover both ports. And then they need access to 3389 because they RDP to something. Okay? And we know their IP address is going to be in the, let's call it the HR network, 10.2.10.x. Okay? That's human resources. So now we know over here, let's take our servers. Let's say that this is our web server. And let's say that this is our domain controller. And then let's say that this is our, for some reason, human resources remote desktop server. HR remote desktop server. Whatever reason, they're RDPing into a box. Okay. Now, they've got to get through our data center firewall, first thing. So we have to have a rule on here that says allow 10.2.10.x to web DC RDP. And these rules will essentially be related to network. So let's say the web server, just to make this simple for everything, web server is going to be 10.50.10.x 2.2. Okay, and the domain controller is going to be on a different network because you obviously do not want domain controllers on the same network as pretty much anything else. You usually keep domain controllers all by themselves. So we'll say that's 10.100.2.2. And then let's say that this server is just some dumb Windows server that somebody had to have and begged and pleaded and cried and you had to build it. So we put that on the Windows server VLAN 200.2.2. And we've kept the 2.2 just because it's simplicity's sake. So we've said that this device can get to from there to 10.50.2.2 80.443. Can get to 10, not 250, sorry, 1050. 10.100.2.2 for 389 and 636, right? And then 10.200.2.2 for 3389. They're going to authenticate via RDP again for some reason. When, why you'd ever split up your firewall from your router. I know various data centers do that, but I've never really understood the decoupling. So the reason you would split up your firewall and your router, from what I have dealt with, is specifically the amount of bandwidth that the devices can handle. For instance, in your home router is usually your firewall, right? It doesn't really handle that much bandwidth. Totally makes sense, right? It's your TV, your refrigerator for some reason has Wi-Fi these days, your computer, your tablet, your cell phone, your gaming consoles, your Steam Deck, whatever you've got, all goes through your router, right? And that's also your firewall. But that takes CPU, RAM, and I/O resources. So it's the ports on the devices, it's the OS that runs, because a lot of systems, which I've showed before, Cisco iOS, that uses resources, and there's only so big of a processor in your routers and your firewalls. So if you make them do both amounts of traffic load, it could be a lot. Because imagine if, for instance, let's say our border firewall was also our router for the entire company, or even just for the building data to get in. Maybe we combine our border firewall and our data center firewall, which you don't do anymore either. That's really been decoupled as well. Because when I started in IT, no one I knew had a data center firewall. They just had a firewall, and that was to let anything in or out of the data center, period. Because the data center had the internet connection, so it all goes through the same firewall, right? Too much bandwidth at a certain point. The devices will overheat, they'll overload, they'll lock up, they'll freeze. You don't want that to happen. So realistically, what you always do is you build, where's the icon again? So you're going to do dual. You're going to do HA pairs for any of this stuff, 9 times out of 10. So we're going to have dual firewalls. And then we're going to take this, connect, oh, sweet. And then that's going to route in. So this device doesn't have to deal with all of the connectivity coming into it. It only has to deal with the traffic that's allowed through. So imagine you have a device, your firewall essentially, it takes in all the packets from your external sources, from what it considers an external source. It's north-south traffic, right? It takes in all of that. So then it has to compute and go, okay, that's got to go to this network, that's got to go to this network, that's got to go to this network, so on and so forth. Well, once it's figured that out, it dumps out what it needs to a router. And then that router can be smaller and can handle the traffic that's already been parsed out and sorted. Because you'll usually probably have a lot of routers, and they will do a lot of different things. So for instance, I don't really have a good server rack design here. You'll have network switches at the top of each rack. They get delegated traffic for all the servers, as opposed to a single switch at the top of your data center for all of your racks that would run out of ports. It's a bandwidth limitation. Sometimes it's a licensing limitation. So maybe you need a firewall that can handle 40 gig, but you know that after the 40 gig link, you're going to go down to 10 gig. You know that you're parsing through enough data after that point that you don't need a 40 gig router. You don't need that level of bandwidth going through your router. So you can get a cheaper piece of equipment that way. But you can still buy firewalls that also do routing, they're just not cheap. They're not cheap by a lot. So all of that to say, it usually comes down to cost. A lot of times it's cost, but it also helps you organize, and it helps you with redundancy, failover. So let's say we've got our two firewalls. They're going to have connections with each other to know that they're in an HA pair. Then you're probably going to have dual core routers that are going to distribute the connections. These are going to be huge, like a Dell 9100. I forget what the Cisco model is, but these are massive. All their ports are 40 gig, 100 gig, 250 gig, whatever. And those are distributing connectivity out to other network equipment across your environment, other switches in your data center to get them 40 gig links to then split down to 10 gig links to each port, so on and so forth. And you could, realistically, if you wanted to, you could buy 40 gig links or 100 gig links for all your servers, and then buy a 100 gig link switch for them, and then have that trail into other 100 gig link server switches and all that jazz and all those routers. But it's not really a justifiable cost. It's too much bandwidth that you're not really using. A lot of people barely saturate 10 gig links. So when you're building out this stuff too, you bring up a good point. You need to consider how much bandwidth you expect to take in versus how much bandwidth you expect to send out, and how much traffic you expect to have to organize. So for instance, if you're an on-prem environment, for example, all of your applications are on-prem, your Active Directory is there, your Exchange server is there, your mail servers, whatever you run there, you have web servers and application servers and database servers. You can get a smaller firewall because you're only going out to the internet for normal stuff, web browsing, and maybe patches for your equipment and your desktops. And most of that traffic doesn't even need to go through a firewall. It just needs to go outbound. It doesn't come in. Some stuff comes in, but you can protect that in multiple different ways. But let's say it's the opposite. Let's say you're a organization that uses only cloud services, only software as a service. So your ERP's in the cloud. You're using Salesforce or Workday or any of those products out there, SAP, out there in the wild. And then your mail is at Google, and your apps are at Google, and you've purchased a web server at AWS. Then you don't have as much traffic coming in at all, but you have tons of traffic going out. So then you have to balance that, like, oh, do we really need that much, bandwidth purchasing for our firewall and router, because most of our stuff lives outside and we don't have to manage it, and it's great that way. DPDK with VPP for super fast routing, but those implementations don't generally have firewalls. Yeah, and again, that's a lot of the more technical side of things. I'm not going to get into that because I'm not going to lie, I don't know it all. I'm not a network admin. I'm going through the basics here of kind of what I've done and what I've seen and what I've learned and how to organize that. So, but that's a great question. Good information. I'll have to Google some of that stuff so I kind of know a little bit more what you're talking about. That's pretty cool. So anyway, back to this. So now we've set up that this network is allowed to talk to this network as long as they all know about each other. And we wouldn't even set this rule up if they didn't know about each other. So we're going to assume that they know about each other. But that's kind of the basics of the first bit of network security. Is you isolate things into separate networks, usually VLANs. You can also get into VXLANs and EVPNs if you really want to isolate the traffic. You can get into software-defined networking if you want to manage traffic in a different way that doesn't require networking equipment, really. It's all software routing, basically, which is really cool. But let's get into VLANs just a little bit. So like I was saying here, we were dedicating these networks to these buildings. We're going to call those VLANs. It's a virtual LAN. That's a way to organize your traffic. So let's say we've got VLAN. We'll call them VLAN. I don't want to call it 1. That's silly. 101. And that's that. Make this a little bigger. Yep. VLAN 1, right? And that's going to be our 10.1.0.0. And then VLAN 102. 10.2.0.0. And VLAN 103. 10.3.0.0. That's going to drive me up a wall. So now we've basically demarked these networks within our environment. We know that that's what these are for, right? So that's the building VLAN. And then it gets kind of crazy from there. Let's say we needed to add a new VLAN within this VLAN. So we'd probably call it VLAN 1011. And you have to be careful with this because you can only have 4096 VLANs. There went my headphones. 10.1.1.0. So on and so forth. VLAN 1012. 10.1.2.0. And then we could the reason you do this is so that you can say camera for whatever reason, printers for whatever reason. Okay. Now we can organize this traffic. Now when we come back to the routing, and maybe we have a print server, right? Maybe we have, let's go over here and let's build a print server real quick. Boom, boom, boom. Print server. And it's on 10.50.3.2. For some reason, the print servers and the web servers are kind of near each other. That doesn't make much sense, but that's what we're doing here. So now our data center firewall can also get a nice new rule that says allow all, because we want the print server to manage the printers. We can just say 10.1.2.0 to 10.50.3.2. We don't really care about the ports or anything right there because we know that those should only be printers. And we know that that is the print server. And if we have multiple print servers, then we would also do a slash. We would do a range. So really it should look like this. It's probably a /24. And maybe we want to have multiple print servers for some god awful reason. So we could do that. But why would you do that? Are you familiar with the ESXi concept of private VLANs? I've migrated to Proxmox recently, but I'm not certain the thing there is topic need to research user. So let's talk about that. I can bring that up. 192.168 20.4. Is that Tiger Host 4? Oh, I've got to do 8006. Okay. So here is my Proxmox host, and I hope I still have this on 50.5. Aha, I do. Oh no, I need 20.5. That's IPAM or iDRAC, sorry. Come on. I'm not going to have much of a routing thing in here. I need that little emoji thing to go away. It's hard to read the chat. Dude. There it goes. And here's the ESXi. So one thing that really threw me when I first started getting into doing networking for Proxmox is it's really different from the way I'm used to doing networking in use your brain in ESXi. So if we go here and we go to network, you have what are known as bonds and bridges and VLANs and devices. In ESXi, you have networking. You have port groups, you have vkernels, you have TCP IP stacks, and you have virtual switches that you can stand up, right? So that took a lot for me to understand. Private VLANs, I don't think is anything I've ever dealt with. We go to the switch, we set up VLANs here. I've never done them without having a trunk being brought in from a network. But in Proxmox, I have actually done software-defined networking, where I have built zones and then deployed VNets within those zones where I create a subnet, so on and so forth, if I need to. So this is like a simple one just for a zone called HPC 10. It was for an internal HPC network so that the VMs could be on there. It's kind of like, it reminds me a little bit of networking in the past. So a long time ago, you would just tell your friends to all get on the same network real quick. It kind of does that next layer of that without having to do much. So I've set that up a little bit in here. This one's a simple. There is the option to do. So if we went and did add, you can do a simple, you can do a VLAN, you can do a VXLAN or an EVPN, and it's all free. It's crazy. We paid a bunch of money to get this functionality in some really nice networking query. But if you wanted to build like a private VLAN, we could just call it private, and we'll use, I don't know what bridge, because I've forgotten what they're called. DMBR0, I think, is one of my bridges. We don't have any DNS servers. We'll hit add there. It'll be cool. And then we'll go to VNets. We'll create. It should grab private. Yeah. We'll call it private. Alias private tag. We're not going to make it VLAN aware, and we're not going to add a tag. We have to have a tag? We do have to have a tag. We'll call it 1000. Right? And now that that is a VLAN, I think we have to create a subnet for it. So if we did 192.10.10.0, and then I believe that's got to be, it's got to be /24 like that, so it knows how many IP addresses to give it. You could hit apply and it would build all this stuff, and you would have an internal network. It was basically a private VLAN. So it couldn't really go anywhere. But if you don't need that traffic to actually leave the host, I think you could make it leave the host. I think that would be the next step. But if you don't need it to ever leave the host, you can just have them talk to each other as long as they're assigned that VLAN. But we're not going to be doing any of that because I don't need it. And that lets you kind of organize your networking in an isolation layer. I would assume you could do that in ESXi just as easy. We don't want to add an uplink. We want to add a network, and I can't remember how to do it. It's been so long. Don't judge me. Port groups. We'll just do a port group. See, it's expecting a VLAN ID here. So I'm really not sure how to add a phone network in VMware, but I'm sure it's possible. Maybe you need another piece of equipment to do it properly. But for an ESXi host, like I said, I'll show you exactly what I've always learned how to do. You have a management network, VMDK essentially, depending on how many trunks you're dedicating to ESXi. So most of the time you want to give one uplink for management network, another uplink for guest networks, and then a third uplink for vMotion traffic, and then possibly a fourth uplink for storage traffic, because you want to organize your traffic and kind of isolate it, work on QoS and things of that nature to kind of organize your traffic. So let's go back to our little terrible drawing here. So we've built our rules to allow things to talk essentially east to west within our environment. One thing I despise with a passion that I see a lot is people will not set up proper east-west firewalls in their server networks. So for instance, let's say we've got this web server here, right? And then that's going to be another web server, and that's going to be another web server. And this one's 10.50.2.3. And this one's 10.52, man, my brain, 2.4. Okay? By default, since these are all in the same network, they can talk to each other. They can do east-west traffic all day long. You could, if this is Linux, for instance, you could SSH from here to here to here to here to here, back and forth. And then you've got an insane connection going on. I don't like this, because what this means is, let's say this one gets pwned. This one gets taken out. It's nuked. It's somebody got in there. For some reason, this had port 80 open to the internet, and somebody found an RCE that got them in. Well, now that this one and this one can talk, because there's no blocking east-west traffic rules, well, then this one's gone, and this one's gone. And anything else on that subnet is instantly gone. And at that point, let's say that maybe this one only talked to that, but this one talk to. Oh, come on. Give me the little arrows. There we go. This one talked to the domain controller. And this one down here talked to this HR remote desktop server. Well, if your hacker figures out how to get into these two, they're going to find that there's a path to get into here and to get into here. They might not be able to get into there right away, but because they've already taken over these 3 boxes, that's a pretty good beachhead. So something that really needs to be focused on a little bit better in a lot of environments is your east-west traffic rules. You don't want things to be able to hop and communicate. Now, if these two need to talk to each other, that's fine, but it should be a firewall rule on the local device. It should be firewall D, allow service, to 7 IP. With Docker and using traffic reverse proxy, I found a solution called Traffic Jam, which solves it though. Okay, yeah. So intra-container communication. Just barely starting to scratch the surface of Docker, and really I'm not even scratching the surface. One of my coworkers is doing great work with Docker containers and things like that. And we have been working on isolated networks for different Docker containers. And it's really cool how all that works, and it is kind of a pain in the butt from what I understand from the yelling and the screaming. But they're doing a great job, and I'm really proud of them. And hopefully I can steal their knowledge and then give it to everybody else. So that's your basics of routing for east-west. And then we've kind of covered north-south a little bit. North-south is going to be internet into you, and then from into you into all this other stuff, and so on and so forth. Your border firewall does a whole lot of work when it comes down to it. It's going to allow in things from the internet that need to get in. So for instance, we're a Microsoft organization. So Azure has to get in. Microsoft has to get in. We need to access Outlook. We need to access Teams. We need to access, Azure VMs. We need to access Azure files, things like that. So that traffic has to be allowed in. But we don't have anything coming from China, for instance. So that traffic doesn't get in. I did hear about the IPv6 CVE. So for anybody watching that has not heard about that, it's essentially like, the way I read it at a basic level is you throw packets via IPv6 and it somehow lets you in. But I also saw that they didn't seem to have a proof of concept that fully worked yet. Like it didn't say that it was in use in the wild. They just said it was possible. And as far as I know, most everything has already patched for it. Another benefit for us, we're not running IPv6. So it would be really hard. You could basically maybe hit our border firewall, but it would just go, where's your IPv4 version? I want that instead. That's what I'm going to give to my users. So as long as our firewalls are patched and our devices are patched, we're good there. But yeah, it basically sounded like a DDoS attack to do a remote code execution, which I thought was kind of funny. And it read, and maybe I'm wrong here, it read like that was almost the intended. No, that was another one. So there's also one about there being a flaw in 0.0.0.0 traffic. Apparently that's another way to basically do 127.0.0.1. Is to just do 0.0.0.0. And you're not supposed to do that. Don't do that anymore. Don't do 0.0.0.0 for anything. You need to do localhost to do 127.0.0.1. That's fine. But don't do localhost either. If you're developing on your local machine and you're in a business, just ask for a web server. Just say, hey, I need a dev web server. I need to develop on a dev web server. So yeah, golly, I think that's going to be about it. This has still been a mess in my mind. I feel like maybe I need to redesign this again. I'd recorded 2 videos about how to do this sort of network discussion, and they both kind of went harebrained. And I feel like this one also went harebrained. But the short answer is organize your networks when you're deploying them. And you know what? You're probably never going to get to do that. You're always going to get thrown into a situation where someone else designed the networks, and they probably designed them 10 years before a new technology came out, and you have to go in and fix them. That's what I've always seen and run into, because when I started in IT, Internet of Things wasn't a thing, and people didn't think, oh, well, I should probably put the phones on a different network from the printers because the printer vulnerability might affect my phones, or maybe I should keep my servers in private ranges instead of giving them all a public IP address. Yeah. Oh yeah. If you're new, this one will blow your mind. In 2 places I have worked at in my life so far, at one point, the majority of the servers had public IP addresses statically assigned to them locally. Not NAT rules, directly assigned to the devices, because that's just what you did. It's just how it was a long time ago. So at 2 places I've worked at, I've been involved in a massive re-IP project to move all of the public addresses off of the servers directly so that we could build NATs for them, or to give the public IP address space back because we didn't need as much, and a cost savings measure essentially there. But that's a thing that used to happen. They would just say, what's our public range? Give it to the servers, call it a day. And then your border firewall was your data center firewall because your border firewall protected your public IP address range. Now you do NAT pools, you let servers talk out. Maybe you set some one-to-one NATs, like perhaps you're running a web server for a big important product that's going to have a load balancer and a lot of other rotating IP addresses because you're going to need to pull pieces out and add pieces in and things like that. That's a whole other discussion for another time. But yeah, lay out VLANs. Understand that you need VLANs for different things. You want to isolate your traffic. If I can't get anything else through to anyone today, always think about isolating your traffic more and more, segmenting. It's a lot of work. It sucks. But when you're able to say, my building computers are on this network, the printers are on this network, the APs are on this network, the networking equipment's on this network, the VoIP is on another network, the cameras are on another network, the networking equipment in the building's on another network. Separate it. SRIOV NICs. I have not played with those. Or at least if I have, I wouldn't know that they were called SRIOV. I'm a good old boy, I guess, when it comes to certain parts of technology. I just know networking goes cable plug in, network go light up, yay, packets. SRIOV NICs. Let's see. Let's just take a look here. Do I have any SRIOV NICs in here? I bet I don't. But they're just regular old VM NICs. Yeah, they sure are. Can I get some information? I forget how little you get access to inside ESXi free. Like how different they organize everything around. Yeah, not capable. Look at that. It's so mad at me. Why is it so mad? Calm down. So yeah, not capable SRIOV. But these are Dell R720s. They're a billion years old, but I love them. I really didn't think I was... I'm one of those people that always left work at work until I was like, you know what? I want to explain and teach to everyone kind of the little that I know. And I'm willing to admit that I don't know that much. I didn't go to school for this. I just got to work in it and picked it up as I went along. So I'm trying to give out the basic knowledge that I have so that folks that are going to school and learning about these things can go, oh yeah, I remember hearing about that in a YouTube video. So that's what this is really about. That's what that means. That's what, proper subnetting and proper so on and so forth is. Before we had a lot of this fancy equipment that takes care of a lot of it for you, we had to just do it this way. We had to do what we had to do. And it still works that way for a lot of folks. Not everyone's going to have the latest and greatest technology. So it doesn't hurt to know the old ways so that you can get yourself in a more secure environment before you can get to difference in technologies, newer equipment, different equipment, things like that. Standing on the shoulders of giants. Yeah. You learn from those who can. Yeah. And I learned from some amazing people in my past, and I'm still learning from a lot of amazing people in my current situation. They're teaching me tons of stuff, and hopefully I'm teaching y'all tons of stuff. But with that, I think we're going to wrap it up for this evening. Tune in soon. I need to actually start making that video. So we had a really interesting outage this past week, and I got the okay to talk about it. And I'm obviously not going to name any names or anything, but it kind of goes into, it's a good example of how you should communicate, how you should test, how you should think, use your critical thinking skills during an outage. And once you find out what caused the outage, how you should consider making changes that would keep that outage from happening the next time. So I'm going to call it something like the IT butterfly effect in before CrowdStrike. Because the short answer is something had happened across the globe from us, knocked our internet access out. And we thought we had done it to ourselves, or at least we had considered that we had done it to ourselves. Then we thought it was our upstream provider. And then our upstream provider found out that it wasn't their fault. It was somebody else on the other side of the globe, and explained what happened. And luckily they got that information. I'm hoping I can find a report or a website or something so I have some actual evidence to give out. But we're going to put all of it in the video, so stay tuned for that one. And thanks for coming by this evening. I don't usually do the live streams. I like doing the live streams though, and I hope you enjoyed it. And we will see you next time.